The model we're going to be building today is going to be a simple fraud detection model. Now, this fraud detection applies specifically to credit card fraud detection. So our model will basically take in a list of transactions, some fraudulent, some legitimate, and it's going to output the percentage at which it can calculate fraudulence versus legitimate, how accurate it is, and if a little bit modified, will output whether or not a specific transaction is fraudulent or legitimate if we pass them in one by one. Now, keep in mind as we go through this tutorial that there are many different ways to build up this particular model, as there are most machine learning models. I'm just going to show you one way in which we can construct it and the way in which I chose. We can build up a very similar model using completely different parameters and output either the same result, a worse result, or perhaps even a better result. And specifically with machine learning models, there's always going to be room for improvement. There's always going to be ways in which we can improve the accuracy until we're at 100%, which is pretty much unobtainable. But that being said, let's get started right away. We're just going to create a new PyCharm project. I have PyCharm open, and as always, I'm kind of expecting that you have the latest version of PyCharm. This is 2017.2.3, and the latest version of Python installed. This is going to be so much easier if you do, as it will give you access to basically all of the packages that we'll need to install and import. Also, if you don't know anything about TensorFlow, we are going to be using a lot of TensorFlow techniques, so be sure to watch our tutorial on the intro to TensorFlow and how to build up a simple computational graph. Otherwise, let's get started. We'll create a new project. The first thing we'll need to do is choose where we want to save this. I'll just create a new folder on the desktop, and it's always a good idea to do exactly that. Just start off by creating a brand new folder. So let's create a new folder here. I'm just going to call this Credit Card Fraud Detection. Okay, click Create, choose that folder. As you can see, it's created down there. Open, Create. And do make sure that you are using the latest version of Python. Even if you have the latest version installed, it might not necessarily be that version that we're using, so be sure to do that. So the rough order in which we're going to do things will be as follows. I will start off just giving a brief overview as to the project as a whole, but basically we'll be first of all exploring the dataset that we're going to be working with. This is actually a pre-compiled dataset, as it's kind of difficult to get our hands on a bunch of fraudulent versus legitimate credit card transactions, and this dataset's already nicely compiled and converted into a numerical format which we can feed into our model. As well, it has a corresponding legit versus fraud outputs as well. Once we're comfortable with the dataset itself, we'll work on manipulating it a bit and we'll do so in such a way that it will be easy to feed into our model and our model can understand and predict with accuracy. Next, we'll work on building up our actual computational graph with a series of nodes and functions that will connect the nodes and help to run basically inputs through that series of nodes. This kind of mini neural network will be building up and outputs either a 1 or a 0, depending on whether or not that credit card transaction is legitimate or fraudulent. And finally, we'll end up with by creating a session, and then we'll be first training our model by running a bunch of data through it, and then testing it to see basically how well trained our model is and how accurately it can predict a credit card transaction. So just want to take a quick second just to say thanks for all the support. We really appreciate that you guys are interested in what we do and continue to support us. I know that particularly these machine learning tutorials do cover some pretty confusing topics. So I've tried to make it as simple for you as I can and explain what's going on at each step. But if you ever find yourself lost, then feel free to go back and watch this section again. And if there are some topics which I don't manage to cover in great enough depth, then definitely go ahead and research that stuff on your own time. It's important to understand what's going on at each step before you continue on to the next one. As like I said, it's easy to get lost, and we're covering some pretty confusing stuff here. But otherwise, I hope you guys enjoy this tutorial. Hope you learn a lot about machine learning and how to build up these models. Again, this is just one of many ways we can do things. I'm just here to show you one way, but once you know how to do the basics of it, then feel free to explore things on your own time. So adjust different parameters, enter in different numbers, so on and so forth. And also be sure to check out some of our other machine learning models that we'll be building too. So without further ado, let's get started with a brief overview where I'll go a little more in depth as to what we'll be doing in this project as a whole. Hi guys, I'm just going to take a couple of minutes here to provide a brief overview of the project as a whole and kind of talk about the order in which we're going to implement our various tasks. So as I'm sure you know by now, we're going to be building a basic credit card fraud detection model, and the end result of this model is that we want to be able to enter a transaction with several of its features converted to various numerical values, and the model will output whether or not that particular transaction is fraudulent or legitimate. Now, a big part about building our machine learning model is going to be obtaining some valuable training and testing data, and we're going to be using this data set found at this particular link. Now, I will copy and paste this link into the Python file at the very beginning once we start learning about it, or feel free to just review this section and just type this particular link into your browser. It should take you right to the data set, which you can then download, but I'll go over with you guys how to do that. Anyway, this is how we're going to be starting. We'll just talk a little bit more about the dataset, how we're going to use it, and what exactly all the values that are passed into this dataset mean. Once we have access to the set, which we'll import into our project, we'll work on manipulating this data into a format that we want to work with. So this will be clipping off unnecessary values, splitting things into X training and Y training, as well as X testing and Y testing values as well. So once we're familiar with the dataset and are happy with the format in which we end up with, we can start actually building up our model, and we're going to do so as a TensorFlow computational graph. This might take a few sections depending on how complex things become. So if you've forgotten the basics of building up our TensorFlow computational graph, I do recommend that you watch our Intro to TensorFlow tutorial, in which I describe a lot of the different components and how they all come together. This will be, at the end of the day, a linear regression model, although it will be a little more complex than the one we build in the TensorFlow intro. So after the model is built, all of the components of the graph have been put together, we can work on actually training and testing our model by creating a new session and then running the particular tensors that we built by passing in some first training data to obviously train the model, and then testing the model using some separate testing data. And our final result would be to output the accuracy of our model itself. And this will be done by comparing the predicted values, what we think we should get, versus what we actually get, or the actual values. Now, as always, this is just one of many, many different ways of building up this model, so I'm not going to guarantee again that this is going to be the most efficient way or the most accurate way of doing things. I'm just here to show you a fairly simple way, I think, of doing things, and just one of the various ways in which we can build up this kind of a model, as well as teach you about the various TensorFlow components and just generally some machine learning techniques in Python and PyCharm. So with that being said, let's move to our first section. Feel free to open up a browser, whatever browser you choose, and copy in this link here, and we'll be right back by learning about our dataset. Hello guys, having provided a brief overview of our project and the steps we're going to take to implement it, we should know that the first step is going to be to become a bit more familiar with the dataset that we're going to be using to derive some training and testing data. So I just open up a new browser and copy and pasted that link that I provided in the overview. So just make sure you'll probably have to type it in manually, but this is going to be the one that we're going to be using, and we'll link to this big data set that provides a bunch of credit card transactions. Now, normally I'd tell you to download it, but I should have provided the dataset to you guys anyway, because otherwise you'd need to actually log in, create an account and all that to download the dataset. So I'll try to include it in some kind of a resources folder or something and make it obvious to you as to where it's stored. I'll show you how to import it into the actual project, as that's going to be the easiest way to go towards the end of this section. So for now, let's just learn a bit more about what the dataset is and what all the values represent. So as you can see, this is just under 285,000 credit card transactions, with just under 500 of them being fraudulent and the rest being legitimate. Now, this is already kind of a problem because, as you can see, only 0.072% of the transactions are fraudulent, which means the data is highly skewed and highly biased towards legitimate transactions. So if we were to use the data as it is, this would cause our model to recognize legitimate transactions a lot more often than fraudulent ones, and would end up producing some pretty skewed results. This is where our data manipulation is going to come in handy, because we'll find a way to hopefully kind of balance this out and equilibrate the fraudulent and the legitimate transaction weightings. Otherwise, like I said, we'd end up with a very biased model. So out of all of these transactions, each one of them is going to be transformed into these 28 different figures, which are all going to be different numbers. And these numbers just represent various features of the each particular transaction. Now, there was some kind of a PCA transformation function that is put in place to convert each of the features into a numerical value, and unfortunately I can't provide more information about the nature of that function itself, which also means that if you're feeding data into the model, then you need to use either the same or a very similar function. That's why the end result of this function, of this particular model we're going to be building, is more on assessing the accuracy of the model than taking in just one or two transactions and outputting fraudulent or legitimate. But that being said, there are some features of each transaction that are easy to understand, the time and the amount, as well as a 1 or a 0 that represent fraudulent or legitimate transactions respectively. So we'll get to know the dataset a little bit more once we start looking at some of the actual numbers involved. So we can now start to think about what we're going to use for our training and testing data, and what we're going to use for our X-train and Y-train, and then X-test and Y-test respectively. So likely, the X-train and X-test will contain some number of these transactions and will contain these features 1 through 28, whereas the Y-train and the Y-test, which is going to be kind of the output, fraudulent or legitimate, will be this either 1 or 0 value matrix. And then obviously we'll take some of the data, most of the data in fact, and set it for our training data, and then some of the data we'll set aside just for testing. We do want to keep these two data sets separate. But that being said, we can now start taking a look at how to import the dataset into our project itself, and then how to import the data as a variable so we can begin manipulating it. So last thing I want to do is just give credit to these guys who've done an excellent job of compiling and composing all of this data into one nice big data set that's easy for us to use. And with that being said, let's just switch on back to PyCharm. Okay, so here we are back in PyCharm. And the first thing we're going to do is just create a new Python file. So this is just going to be under our main folder here. I'm just going to go on New, create a new Python file. And this one we can just call something like fraud detection model. Now, unlike the image recognition one, make sure this is a Python file, by the way, we'll click OK and create that. Unlike the image detection model that we built, hopefully you've watched that one before this one, we're not going to be separating the model itself into a training file and then a testing file and saving the model like that, just because there's not actually that much training that we're going to need to be doing. We're actually going to store everything in just as one file, so every time we run this, we're training and testing it, and I just want to do this to show you both ways of doing things. As well, like I said, the output is more geared towards how accurate the model is and how accurately it can detect fraud versus legitimate transactions, rather than taking in one specific transaction and outputting fraudulent or legitimate. Although, like I said, if you can find that same function that they use to transform the data, then that will be, our model will be able to do that for you. But otherwise, we're just going to show you how to add the CSV file into your project and then how to store it in a variable. So I have saved my CSV file just under my desktop here. Okay, but like I said, I think I will have placed yours in a folder called resources. Either way, the file itself will be called creditcard.csv. And it's basically just a CSV file, which is kind of like an Excel file if you have used those, which is just a big data sheet. Okay, and we're just going to simply drag and drop it actually right into our project. So just oops, not really wanting to click there. Just make sure you have it selected and just drag and drop it into this folder. It will ask you to move it, and you can either copy it or you can actually just move it directly. Let's just click OK. So if you really wanted, you could keep it in that resources folder. Just make sure that when you're providing the path name for this file, you are providing the path name to the location of that file. Otherwise, it's much easier if you just take it right into the project. Now, in order to gain access to this file as well as be able to manipulate it easily, I'm going to import pandas. Okay, and I'll do so as PD. And pandas is basically a library that gives us access to a lot of big dataset manipulation functions, which just make it really easy to take in a file, store it in a variable, and then perform various manipulations on it, such as separating the dataset into XTrain and YTrain data, as well as a lot of other manipulations. So we're just going to store the results in something called credit card data. Okay, and it's just going to be equal to PD.read CSV. Okay, nice function there already for us. And all we need to do, if it's imported into the project, is going to be to provide the actual CSV file name. It's just creditcard.csv. Make sure you do add the extension, so creditcard.csv. Now, like I said, if you wanted to keep it in your resources folder, make sure you're providing the actual path name to it. So, maybe like resources -creditcard.csv or whatever it would be, rather than just the name, as I can provide just the name because it's already part of the project. So I guess we can just save this and actually run it just to, get a quick look at what the data actually looks like. Alternatively, you can just double click and open this. If you have something that reads CSV files, that's all good. Otherwise, we can go to our run window, we'll select the run option, and we'll make sure we're running our actual fraud detection model file. Okay. Now, like I said, this is just going to, that's actually going to read it. It doesn't have anything to output it, so we can just print out our credit card data and give it a rerun, and this should just kind of print out all of the stuff here. It's probably not going to print every single row and column. It will kind of end up truncating the data, as you can see. So just going to take a look at this, recognize that we have first the numbers column, time column, and then the features 1 through 28. I'm not sure where it is, where it ends up. Yep, and then the amount, and finally there should be a class as well. And here it is, a class either 0 or 1 for each of those transactions. So I would recommend taking a moment just to understand the dataset a little more. And I'll explain as we go exactly what each component of the dataset is doing for us anyway. And our next section will be dealing with actually manipulating this data, separating out the pieces we want, and storing them in respective variables so that we can better build up our model. Hello everyone, this is where we left off in the previous section. We'd learned a little bit more about the dataset, we'd imported it into the project here, and I've just stored it in this variable credit card data. After we ran it and printed everything out, it outputs pretty much the whole dataset, just truncated a little bit, as you can see with these dots. So hopefully you had a look at it, kind of understand what's going on. I'm not expecting you to understand what these numbers mean exactly in the columns V1 through V28. But just understand that at the end of the day, these columns, v1 through v28, are going to be our inputs, and the class columns, which if we scroll down to the bottom, you see this class that has either a 0 for the legit ones or 1 for the fraudulent transactions. Those are going to be the outputs that we want. So that's actually what we're going to be working on in this section, is splitting our big data set into 4 smaller sets. One is going to be for the X test, one is going to be for the Y test, one will be for the X train, and one will be for the Y train. Once we have these data sets split apart, we can work on actually manipulating them to hopefully eliminate that bias that I talked about earlier, in which we know that the data set is very heavily favored towards legitimate transactions, and that could really screw things up later on. But we'll save that for the next section. Let's just work on breaking our data set apart into, again, the training and the testing data, and then into the inputs and outputs. So as you can see, I've just added this comment here. It just says import and stored dataset. That's just what these couple of lines are doing. We can actually get rid of this print statement if we want. And I think this is what I'm going to do at the end of each of the sections we cover. I'll just kind of annotate what we've gone over in the previous section, so that when you start up the next section, you have all of the previous stuff annotated and you know exactly what those lines of code are doing. Because especially once you get to the end of the project and try and look back, if you don't know what a single line of code is doing, then that can really confuse you for the rest of the project. So if you see all these extra comments and stuff, that's what I'm doing. I just don't think it's very practical for me to spend a lot of time typing these comments out while we're recording. But that being said, let's get to work. So splitting the data up is going to require about 6 different steps. Some of them will take a little more work than others. But to start off, we know we're going to need some of our NumPy functions, which again give us the ability to manipulate data inside of arrays and big data sets. So we're just going to import NumPy to start, and I'll import it as NP. Okay, and before I write any code, let me just make a few quick comments. So step number 1 to separating out our data is going to be to shuffle or randomize the data. So shuffle / randomize the data, okay, and this will just help to break up any annoying and unwanted clumps. Okay, next step is going to be changing our class data to what's called one-hot encoding. I'll explain why we'll need this in a second. Basically, it's just a way to input the data into a nicer form into some of our functions, such as the softmax or the dropout functions. They like this one-hot encoding. Okay, so step number 3 is going to be to normalize our data. So if you look to the data set, a lot of the values are negative. Some of them are greater than 1. We just want to convert everything into a value between 0 and 1. This just makes the data a lot nicer to deal with. Okay, so step number 4 is going to be splitting up X and Y values. Okay, so as I'm sure you know from the previous tutorials, X values are typically our inputs and Y values are our outputs. So like I said earlier, the X values are going to be those columns V1 through V28, and our Y values are going to be, after our one-hot encodings, the outputs that are going to be basically each a matrix of 0 and 1. Again, I'll explain why after our one-hot encoding. But basically, the Y values are just going to be whether or not the transaction is fraudulent or legitimate. After this, we'll want to actually split our data into those 4 sections, but before we can do that, we want to convert the data frames, as they're going to be called up until this point. So this is called the data frame. So we're going to convert data frames to NumPy arrays. Okay, and this is just going to be a little easier to work with. Specifically, we'll do float 32s. This will just require 1 line of code. As I'm sure you know, TensorFlow does like to work a lot with float 32s. Okay, and finally, number 6 is going to be the final task. This is just going to be splitting the final data into our X/Y train /test, and this is just going to be basically the 4 different sections. So we'll have X train and Y train, and then X test and Y test. And this whole process is going to be gearing towards splitting data into 4 sets. Okay, so let's get started. And again, our first step is just going to be to shuffle or randomize our data. So I'm just going to store the results in something called, I don't know, shuffled data. Okay, and this can just be our current data. So this is stored in credit card data, and we're just going to call on this function called sample. Let me just pull that up. Okay, sample here. For some reason it's called sample. This just basically shuffles the data. I'm just going to enter in one parameter, frac equals 1. So this is just a fraction of the data we're dealing with. In this case, this is just going to be 1, which means all of the data. So we're basically just going to shuffle it all around. Okay. So next up is our one-hot encoding. We can store this in something called one-hot data. Okay, and this is just going to be, we're going to call on actually a built-in pandas function called pd.getDummies. And what getDummies is going to do is it's going to take in a data frame. In this case, it's going to be our shuffled data. Okay, and it's going to ask for a column that it wants to split into one-hot encoding. Well, that column, if we zoom out and take a look at our data, is going to be our class column. So again, we want to convert these into, because right now they're in a format like this, 0, or, oh, actually, wrong kind of comment. It's either 0, or a 1, well, we want to actually convert this to a form that looks a little more like this. 0, in the case of it being legitimate, in which case it's a 0, we'll want a 1 and a 0. And in the case when it's fraudulent, we'll want something like this, a 0 and a 1 instead. Like I said, this is just going to provide us a better way to feed this into some of our functions a little later on. So we need to specify that we're going to be breaking up our class column. We can do that by calling on columns equals, and because it might take in multiple columns, we'll put this in an array and we'll just pass in the name class, which will again split up this class column into this format here. Next up, step number 3 is going to be to normalize our data. So again, this is just taking everything and breaking it into, or converting it to a value between 0 and 1, just feeds better into our models. So I'll call this something like normalized data, okay? And this is going to just require some basic calculation. So we'll take our total data here, which in this case is just going to be 1 hot data minus our 1 hot data of the minimum, so .min, okay? And let's just open and close these brackets here, okay? And then we're going to divide this by basically the max minus the min, so 1 hot data dot max, okay, minus 1 hot data dot min, okay? Again, this just converts it nicely into a format where everything is between 0 and 1. Okay, next up is going to be splitting up our x and y values. I guess I should probably zoom in, as it might be kind of hard for some of you to read if it's super zoomed out. And as we know, our x values are going to be basically all of those columns v1 through v28, and our y values are going to be basically just as one hot data column, which in this case is just going to be the class 0 and class 1, as it will be called once it's split up. So we can do this over 2 lines, but it's easier just to do it over 1. In fact, you know what, let's make things a little more readable for you guys. Let's just do it over 2 lines. So let's deal first with the x data. So let's call this df underscore x, and usually they like the x to be capitalized. This is just going to be our normalized data, and we want to call this .drop function, which is basically going to take in a column name, and it's going to drop all of the data, or it's going to keep all of the data and drop just the data in that column. So in this case, after we have converted our data into 1 hot data, it's going to, the class column is again going to be split into 2 classes, one called class underscore 0 and one called class underscore 1. So rather than just passing in class like this, we'll have to pass in class 0, okay, and we'll also have to pass in class underscore 1. So what I would do if you're unsure about why this is popping up is after each of these stages, just kind of comment out the rest of the code and print out each of these lines. So after you've shuffled the data, print out the shuffled data. After you've converted everything to 1 hot data, then print that out. After you've normalized it, print that out. And keep doing this until you've got a grasp on exactly how each of these manipulations is changing the data that we're dealing with. It's much easier, of course, to understand what's going on if you can visualize what each of these changes is doing. Okay, we're just going to enter in actually one more parameter. It's just going to be axis equals 1. And then because we have our x values, we'll need our y values also. We could just go df underscore y. This is basically just going to be our normalized data. And instead of calling the drop, we actually do want these in here. So we don't drop them, we just get these. So we'll call on our array at a specific index, and the ones we want are just going to be class underscore 0 again, and class underscore 1. All right. So again, could have done these in one line by saying df underscore x, comma df underscore y equals this, comma this, but this is just a little easier to read. Okay, so after this, we'll want to, we've split up the x and y values, so we want to convert our data frames, or these guys here, into our NumPy float32 arrays. That'll be simple enough. We can do array underscore x or something, and set this equal to np.asArray. Okay, so this is going to be a NumPy array. We want to specify what values we're going to be using. In this case, it's just going to be the values of this particular data frame, so we'll go df underscore x dot values. Okay, and we want to specify some kind of encoding, so we'll just go float32. I guess we'll specify a data type, so dtype equals float32. And we'll do pretty much the same thing for df underscore y. Let me just show you that syntax I was talking about earlier, just in case you've never seen it. So you can go df underscore y equals, and then just add a comma here. And then we'll basically just take this, copy, and paste. And instead of doing the df underscore x values, we want the y values in the same encoding float32. So it'll just be basically, oops, I think I accidentally got rid of something there. Yeah, I did. So it's just basically taking what we would have done over 2 lines here and just setting it all on one long line. So I know this is a bit harder to read, but it just takes up a few lines of code. Alright, and the final step here is going to be splitting up our data into these 4 sets, okay? So we've already split the data into 2 sets. We have all of our x values and all of our y values, but we want to go one step further and split probably about 80% of these into the training, and then the remaining 20% can be testing. So actually, let's just create a variable that will represent the training ratio. let's just call this something like train size. So train size is going to be equal to 0.8 or 80% times the length of our data, or the length of array underscore x or y, it doesn't really matter. And at the end of the day, we want to make sure this is an int, so I'm actually just going to encompass this in brackets and put int here. Just make sure, again, it's an integer form. And now we can just use ranges and our upper bound and lower bound to allocate the certain parts of the data that we want into, again, the training and testing data sets. So just because this is going to be hard to see if we're all zoomed in, I'm just going to zoom out. And we'll call the x and y values raw x and raw y values. So we'll start off with a raw x train, okay? And you know what, let's put in tuple. We'll have a raw x train and a raw y, that should be lowercase y train. We're going to set this equal to this tuple here. We're going to put in our array x, array underscore x, okay? And we'll want a range, and then we know we're going to want our array y. And what did we call this? Oh, I put df of y, that's weird. Sorry, this should be array underscore y. Okay, we want array underscore y of a particular range also. So it will go basically, let me just make this easier to see, from 0, so nothing on the left hand, up until our training size, and then again from 0 up until our training size. This will now store 80% of our total data into our x train and y train. Okay, and then we could do the same for the x test and y test. Again, if you want to put it all on one line, you can. I'll just put it under 2 lines to make it easier to read. So actually, you know what? Let's just copy all of this. That was why I zoomed out originally, because I actually usually put them on just the one line like this, and it makes for a really long line, but you know, let's make things easier for you guys to read. So this will just be our x test and our y test. Okay, and we're going to go, instead from 0 to train size, we'll go from train size to 0, or to the end of the array, and then again from train size up until the end of the array. Okay, and again, this is just allocating the first 80% to these guys here, our x train and y train, and then the remaining 20%, which will be the last 20%, to our x test and y test. And then there's another reason why we shuffled up the data, so that we're not guessing any kind of a bias again, and hopefully that will kind of just randomly distribute all of the ones and zeros. So there you have it. At this point, we have successfully split our data up into our 4 values, our training and testing for x and y, and actually, yeah, all of those 4 values there. Again, if it's unclear at any of these steps along the way why we're doing each thing, then just kind of print out the end results of each of these. So for example, after we shuffle the data, maybe do something like print shuffle data, okay? After we've taken the one hot data, maybe print the one hot data, and so on and so forth. And once you can actually visualize the changes in the dataset, that makes it a lot clearer as to why we're making these changes, and so that when we come to manipulate the data a little later on and change up the values into the format we want, it'll be a lot clearer as to why we're taking all these steps and exactly what data we're dealing with when we're dealing with the x train, or the y train, or the x test, or the y test. But otherwise, because we split the data up, we can end this here and move on to the next section, which will be manipulating stuff. Again, I'll kind of annotate each of these lines anyway, but do check them out for yourself. It will really help to make things easier to understand. Alright, so we just finished separating our big dataset, the credit card data, into our 4 mini datasets. So about 80% of the data is allocated to our X training and Y training datasets, and then the remaining 20 is allocated to the X test and the Y test. Now, despite some kind of transformations we've done, we're still left with the issue that our dataset is very, very heavily biased towards legitimate transactions. So this is a big problem when we're trying to train our model, because our model is obviously going to see a lot more legit transactions, and so when it comes time to test the validity of the model, it's more likely to say that a transaction is legitimate versus fraudulent, even though it might be fraudulent, just because that's what it's been more exposed to, that's what it's had more time to learn about. So what we need to do is devise a clever way to basically make our model take more notice of the fraudulent transactions, and that will hopefully help to eliminate the bias at least a little bit. Now this will be done through a process called logit weighting, and it's actually quite a simple process and very practical. We'll get back to that in a second. I just want to take a moment to print out exactly what kind of ratio we're dealing with, so that hopefully you guys will gain a better understanding of the gravity of the issue. So you can follow along if you want, or you can just watch me write these few lines of code. It's basically just going to be printing out a ratio of fraudulent versus legitimate data, and I just hid the run window, which is why things might look a little different from before. So I'm just going to create a couple quick variables. I'll do like a count fraud. No, let's do legit first, and then a count fraud. Okay, and this is just going to be np.unique, which will get all the unique elements off an array. The array is just going to be our original credit card data. I'm not going to take any of the modified data sets. Okay, and I'm looking for the column class. Okay. As this is going to be the main way in which we're going to be able to tell if a transaction is legit versus fraud. Remember, legits have, before the one hot encoding, a value of 1 in the class column, and fraud, or legitimates have a value of 0 and fraudulents have a value of 1. Okay, so we also want to return count, so I'm going to set that to be true, and we are looking for the index 1. So this will separate basically our legit transactions into all those that have the value 0 and our fraud into those that have the value of 1. Okay, next I'll need some kind of a ratio so I can actually print out the percent. So I'm just going to call this fraud ratio. Okay, and this is basically just going to be our count fraud, okay, divided by the total amount of data, so count legit plus count fraud, okay, and I can convert this, I guess I'll convert this into a float, okay, so just wrap this whole thing in a float, and then at the end I'm just going to print this out. I'm just going to print something like legitimate, you know, I'll say something like percent of fraudulent transactions. Okay, and I'll also add in the actual fraud ratio here. So if I were to now go ahead and run this, this is just going to print out some very small percentage that represents the number of fraudulent transactions versus the number of legitimate transactions. So as you can see, this is actually the percent. So this means this is basically 0.172% of transactions that are fraudulent. So this means that about 99% of all of the transactions our model will be exposed to as of now will be legitimate. So you can see that our model will very heavily favor the legitimate transactions. I mean, think about if you were tasked with telling the difference between two objects, and you basically only saw one type of the object and almost none of the other type of the object. Well, at that point, it's very difficult to tell that the other object might be indeed different from the first one, okay? However, if we placed greater importance on object 2, even though we might have seen it a lot fewer times, it'll be a lot clearer in our mind as it will have a higher weighting. It will stand out a little more. So we'd be a little more likely to recognize it. And that's the whole idea behind this logic weighting, is that instead of just having like a 1 and a 0, as we did with these one hot encoding tensors, we're going to multiply these by a certain amount, and that will introduce what's called a higher weighting to our fraudulent data. So for example, let's say that before this logic weighting, I have just the 1, 0 for legitimate data and then the 0, 1 for fraudulent data. After logic weighting, I might have, let's say I multiplied by some constant 10 or something. My fraudulent data would have a weight of 0 and 10, instead of 1 and 0, so then because this is a higher number, a higher weighting, our model will pay a lot more attention to it when it's being trained, so that it's more likely to look out for those numbers when it's actually being tested. So as for the actual constant we're going to be multiplying by, I think I'll go with 1 over this fraudulent ratio, so basically 1 divided by 0.172. And I'm just going to store the results in some variable here, and I'll literally just call this a weighting. So weighting is going to be basically 1 divided by our fraud ratio. So maybe it's a good idea that you actually take a moment to type this stuff out, although you don't have to print it if you don't want. And this should give us a number, I think of, it's a bit over 500, might be closer to 600, I think it's like 570 something. And we'll basically multiply all of our Y training data by that value, so that any time it sees a 0 and 1, it's going to multiply that 1 by, in this case, about 570 something, just whatever the weighting number is. We don't, however, want to multiply our legitimate data, or else that defeats the entire purpose of applying a heavier weighting to our fraudulent data. So this is a very common technique used for very unbalanced datasets. Obviously, it's much better to deal with a balanced dataset, in this case just due to the nature of having a lot more legitimate transactions than fraudulent transactions in general. It's kind of hard to, it's a difficult issue to get around without resorting to this technique. So we're basically going to have to get our raw Y train. Okay, and now we're going to reassign it, and actually we'll need specific parts of it. Okay, so we'll need basically all of it, but we're only interested in the ones. Or basically any time it will see a 1 in the right hand column, which again indicates fraudulent transaction, well, we're just going to set this equal to Y train. We'll pass in again the same thing. Okay, and we're going to multiply this by our weighting. Okay, so that actually takes care of the issue pretty much for us. And that's just about all we really need to do to hopefully eliminate the bias. It's not going to eliminate the bias completely, but again, because this number is going to be quite high, our model will pay a lot closer attention to the fraudulent transactions than to the legitimate ones when it comes time to actually train and recognize what is fraud and what is legit. Okay, so just a very quick summary before we move on and actually start building our model. Because our datasets are heavily biased towards legit transactions, we have to apply a weighting using a technique called logic weighting to our fraudulent data. And basically we just got the ratio of fraud to legit. It spits out this very small number. We're just applying a weighting of 1 divided by that, so it sets it to a larger number. And then we're multiplying any time we see a fraudulent transaction, so a 0, 1 instead of a 1, 0 in our 1 hot encoded data. And we're multiplying that by our weighting so that we're going to, apply a heavier weighting to our fraudulent data so the model will pay closer attention. So with that being done, that's pretty much all of the dataset manipulation we need to perform, and so we're ready to start building up our actual testing model, or training model, I suppose. So this will be done over a few different sections, as I don't want to kind of overload you guys with too much information at once. As always, I'll keep annotating things at the end of each section. I'll add some comments here. As you can see, I've added a bunch of comments to the stuff we did in the last section. And so I'll continue to do so. So let's actually get started on building up our computational graph. Hey everyone! With the application of our logic weighting, we've hopefully eliminated or at least minimized the bias between the legitimate and the fraudulent data. And we have our big dataset separated into these 4 mini datasets. And so now I think it's time to start actually building up our computational model, starting with the construction of the actual graph itself. So this is basically going to be a few layers of several different kinds of TensorFlow nodes. And it's going to be quite a little bit more complex than the simple linear regression model we built in our TensorFlow intro. Now, because it's going to be quite a bit more complex, the reason being that this is a much more complex issue to deal with than what we had dealt with previously, we're going to be building this over a few sections, but the underlying principles remain the same. We're going to have some kind of input. In this case, we'll actually have a few layers rather than just one. We'll have some kind of an output, and the idea here is to count up the loss and to minimize that loss over several different epochs. If all of these words are completely unfamiliar to you, then I really recommend you watch our Intro to TensorFlow tutorial, just so that you are not completely lost in the next few sections. And as always, I'm going to annotate everything at the end of each section, and I'll try and go a little more slowly and separate things out so that you have a break between each of the different sections. But otherwise, let's get started with an import for TensorFlow, of course. So we want to import TensorFlow. I'm just going to label it as TF so that we gain access to all of the TensorFlow functionality. By the way, I just minimized the run window here just to give ourselves a bit more room. As we're kind of running out of space, it's getting a bit cluttered now. So the first thing we need to do, or well, we might want to do, is just to define a few constants that we're going to use throughout. So we'll need some kind of an input dimension and some kind of an output dimensions. So we'll say the input dimensions, I'll literally call it that, okay, are going to be the shape of our input array. In this case, it's going to be basically the 30 units that are in our XTrain dataset. So I know the XTrain dataset contains many, many different rows, but it only has about 30 columns, the V1 through V28, plus there's a time and an amount column. We'll want those as well. So we want, instead of the raw XTrain, we're actually going to use the array_x, which is just before the actual allocation of the training and the testing data, although to be honest, it probably doesn't really matter anyway. But we'll go, actually no, we don't want NP, we want our actual array itself, and we'll go .shape, and we want index 1. So this will now be basically an input of about a tensor of 30 elements, so that we can input any one of the raw X train or the raw X test as we feel is necessary. So obviously training data, testing data. Okay, and the output dimensions themselves will just be 2 units wide, because we are going to be outputting that 1 and 0 value that we saw here with the hot encoding. So we're just going to set the actual output dimensions equal, just put the S there, equal to our array_y.shape, and again we want 1 from there. Next I'm going to add a couple more variables. We might not necessarily understand why we're using these numbers yet, but just bear with me here. This is basically just going to be specifying the number of cells we want in each of our layers. So we know the input layer is going to be just the 30 cells. The output dimensions are just going to be the 2 cells. And then in each of the middle 2 layers, we are going to have 100 and then about 150 cells. So I'm just going to call this variable something like num layer 1 cells. Okay, and spelled that wrong. Okay, and I'm just going to set this equal to 100. And then we'll go num layer 2 cells. And we're going to set this equal to 150. Okay, so with these values, we're going to now create some actual input tensors themselves. So these are going to be basically tf.placeholder type nodes. Okay, so I'll call this something like x_train node. Okay, and this is going to be tf.placeholder. And we basically want this placeholder to be the input dimension shape, as we're going to be, because it's the X train, this is going to be taking in some kind of input. So we want these to be tf.float32. We again want the actual tensor itself, so we're going to have this none by input dimensions. So about 30 columns here. Okay, and I think I'll give this a name as well. Just going to set name equal to, how about, let's just call it X train. Okay, and we're going to do a very similar thing for our input or our Y train. Okay, so just going to copy that and paste it. This time instead of X train, it's going to be Y train. And again, a similar thing, except for our input dimensions. We obviously don't want it to be 30 units wide. We only want it to be 2, so it's just going to take in output dimensions instead of input. So output dimensions there, and we definitely want to change the name as well, so just going to call it Y train. So these are basically going to be, these nodes are going to be used for training, so that when we go to run our actual session, we're going to need to pass in values for our X and Y train nodes. And I'm sure you guessed that we're probably going to end up using our raw X train and our raw Y train data sets for these. Now, because we've created our X and Y train nodes, we need to create some X and Y test nodes, and these we can actually just allocate to be constants because we have our actual testing dataset here, raw X test and our raw Y test. If you want to pass in different values, I'd recommend you either create placeholders or some kind of variable nodes, and then you can assign the value at a later time. Also, if you want to test cases one by one, then again, you'll definitely want some placeholder node instead so that you can input values at runtime. But otherwise, we're just going to set an X test node. Okay, and it's going to be a similar-ish thing, except instead of a placeholder, it's just going to be a constant. We'll pass in the value of our raw X test. Make sure it's the X test, not anything else. And I'll give this a name of, let's see, we had X train, so let's just give it the name of X underscore test. And we'll do pretty much the same thing for the Y. So let's just copy and paste. I'll call this Y test node. tf.constant. We want to take in the raw Y test data, and again, name to Y test. Now this is where things get a little weird. I'm just going to zoom out so we can hopefully see the bigger picture, as kind of hard to see when everything's so zoomed in. But we'll basically be building up our other layers next, okay? So these you can think of as being the inputs into our model. And now we'll need to build up layer 1, okay, number of this cells, layer 2, and then finally our outputs, our output layer, which will kind of take on this dimension. Now for each of these layers, we're going to need the weights of the layer as well as the biases of the layer. And each of these I'm going to set to variables because their values will be changing as we're trying to optimize the loss. So here goes layer 1. I'm just going to call the first one weight 1 node. Okay, and it's going to be TF. This time it's going to be a variable, remember capital V. And we'll basically start out our variable node with an array or a matrix of zeros. Okay, so actually I'll do TF dot zeros. Okay, so it's basically going to be a matrix of zeros. We have to specify the dimensions. In this case, we'll just have the input dimensions first, okay? And then we want our number of layer 1 cells, so num layer 1 cells. And I'm just going to give this a name, probably best to, where possible, give these guys a name so you can identify them by name rather than just relying on this variable here. So in this case, I'll call this something like weight 1. Okay, and that's all we need to do for the weight 1 node here. So at the end, it looks kind of like this, and this is why I zoomed out, just because I can't really fit everything in this zoomed in window. So it's just a variable node. We're basically setting up a matrix of zeros. This is going to be, in this case, about 30 by 100, I believe is, yep, that's right. And the name is just weight 1. Now we'll need to create biases 1 to match this. So I'm just going to call this biases 1 node. And this is going to be another variable, so tf.variable node. We will start up an array again. This time tf.zeros also, but instead of this matrix, we're just going to have it be a single dimension array. And that array is just going to be our number of layer 1 cells. And we'll give it a name as well, so name, I'll just call this something like biases 1. Now we'll need to do a very, very similar thing to this in our layers 2 and 3. And again, I'm not expecting you to understand exactly what's going on right now. As I said, I'll kind of annotate things as I go at the end, and everything will come together, and it will be a lot clearer towards the end once we can see the big picture here. So I'm actually just going to copy this, paste, and we're going to modify these. So this will be 2 and 2, and this will be 3 and 3, or output, whatever you want. It's up to you. So in this case, instead of input dimensions and the number of layer 1 cells, we're actually going to have number of layer 1 cells and then the number of layer 2 cells. And then we're going to do the 2 down there. We'll give these different names. This is going to be weight 2 and biases 2. And actually, I'm just going to change the names right now. Biases 3. Okay. And then similarly, we're going to do number of layer 2 cells. Okay. And then this one is going to be just our output dimensions. Okay. And the node, the biases node 3 is going to be our output dimensions here, and just make sure the names are all going to match. So hopefully you can kind of see what's going on here. We're basically having the input and our number of layer 1 cells, and then the biases is matching this, okay? And then we're having the number of layer 1 cells by number of layer 2 cells, and then of course the number of layer 2 cells, and then we have number of layer 2 cells and then output here. So every layer is just kind of connecting together here. So except for the output, which will just be its own kind of separate thing, we can almost think about these as being the output of one layer is kind of the input of another layer. So that's why I created the constants up top rather than just feeding in actual values, because if for whatever reason I decide that my model's not good, I want to adjust the number of cells, then I can basically just change these numbers here without having to change everything. Now, each of these are variables because right now there's just basically matrices of zeros, and we don't want them to be zeros. I mean, that's not very useful to us. Our goal is, again, to create some kind of a loss. We'll use a different loss function than before. We're trying to optimize that loss by adjusting the values that all of these have. That's why they're variable nodes instead of the constant nodes, which are going to be our actual test cases, and the placeholder nodes will assign values at actual runtime. Now again, finding out exactly how many layers we want, in this case we have 3, and the number of cells in each layer is a bit of an art and can take a lot of trial and error. Also, it's purely dependent on the task we're trying to achieve. When we were doing just a very simple linear regression before, it was easy to accomplish with just the one layer of cells. In this case, we're actually doing something a lot more complex. We're working with a much larger data set, so we're going to need to go a few layers deep. And as always, as I said right at the beginning, and I'll probably rehash this lots of different times, this isn't the only way of doing things. It's just one of many different ways where we can build up a model like this. Okay, but otherwise our graph is well on its way to being built, so we're going to want to start building up our actual training and testing functions. And a nice way to start to optimize the amount of loss, or rather minimize that loss, by creating some kind of loss function, minimizer, and a bunch of other functions. So basically the graph is almost constructed now. We have all the components necessary, but we need some functions to actually bring everything together and to call upon once we're running everything. So that's what we're going to do in this section coming up. We're just going to be working on building those functions. We might take a couple of sections depending on how long it's going to take, but otherwise I'll annotate what I did here, and just be sure to review it and understand what's going on, at least kind of roughly, before we move on to the next sections. Hey guys, by this point we've built up a few of the components of our computational graph. Specifically, we have some inputs for our training, we have some inputs for our testing, as well as we have a few layers built up. So the first layer is actually going to take in the input from the user, then we're going to pass it through the second layer, then through the third layer, and by the time it finishes at the third layer, it will actually output some kind of a tensor, which will be able to tell us whether or not the transaction is fraudulent. Of course, we'd have to run this through for every transaction, but we're not going to do that just yet. We'll save the actual testing or training and testing portion for 1 or 2 sections from now. What we'll do in this section is add in a few functions that will help to regulate the flow of information through these 3 layers. So we'll start off by creating a function that will take in some kind of a tensor as an input. It will run that tensor through these 3 layers, and then it will return another tensor, which will be kind of the result of several different machine learning functions. And this just kind of helps us to fit the data. After we've done that, we can add in stuff like a way to optimize the amount of loss. So we'll need first a loss function, then an optimizer, and then we'll add in 1 or 2 other little bits and pieces. So let's start by creating that networking function. And you know what? I think I'm actually literally just going to call this a network, okay? Because that's kind of what it's doing. It's running our input through this neural network. So it's going to take in an input tensor. Okay, and this could be, for example, our training nodes or our testing nodes. Either way, this is going to be a nice way to kind of predict what our output should be. So we'll have to run it through 3 different layers. We'll start off by creating the first layer with some kind of a function, and this is going to take our input tensor, it's going to multiply it by a bunch of stuff, and it will output something, okay? Then we'll use whatever it outputs, so layer 1 as an input into layer 2, we'll do the same thing, or probably using different functions. Then the output of layer 2 will be fed into layer 3, and then the output of layer 3 is what our function is going to return, okay? So we'll start off with a layer 1. And we're going to use some TensorFlow functions. So tf.nn is the TensorFlow.neural networks, and we're going to start off with a sigmoid function. Now, there's a few different functions we could use. I chose sigmoid because it is a good function that fits the data well. It's kind of hard to see what function we should choose that provides the best fit without an actual graphic visualization of the data. So if there's some way you can take that CSV datasheet and actually graph it, or perhaps the modified data, so this stuff up here, the raw Y train, raw X train and stuff, if you can find a way to actually graph that and fit a line through it, you'll see that sigmoid is a good function to actually do this, provide a well-fitting line. So this will basically be the results of some matrix multiplication. So we'll call on a tf.matmul function. or matrix multiplication for short. Okay, and we want to multiply our input tensor by the weights1 node, which is the first layer. So we'll do the comma here, weight1 node, and this is just going to multiply these together. And then, of course, we want to add our biases, so plus biases1 node. Okay, and that's actually all we need to do for layer 1. Now, we'll actually do a pretty similar thing for our next couple of layers, except that instead of taking in the input tensor and multiplying that by the corresponding weight, so 2 or 3, we'll actually take the results of layer 1, so layer 1 itself, and then multiply that by weight 2 node, and then in the layer 3, we'll take layer 2 and multiply that by weight 3 node. But for the next layer, we're actually going to do something slightly different. We're going to use what's called a dropout function, and this helps prevent our model from becoming lazy. So this is kind of a weird concept in that if the model is right too many times, then it kind of becomes lazy because it thinks, I've been right this many times, I'm going to be right in the future. So with the dropout function, this helps to cause the actual model to keep paying attention to the data it's given. So we'll set layer 2 equal to, we'll start off with tf.nn again, and then instead of sigmoid, we'll do a dropout. Okay, and then within the dropout, we'll do another sigmoid function, and then we'll add the actual kind of decimal that will, or the decimal number that will represent the amount of dropout we want to add. So we'll do a tf.nn.sigmoid. Okay, and in the sigmoid, we want to, again, use our matrix multiplication. So we'll do tf.mapmul again, and instead of the input tensor, of course, we want layer 1, and we want to multiply it by our weight 2 node. And then, of course, we want to add the biases, so plus biases 2 node. And then also, because we're still inside of our dropout function, we need to specify exactly how much dropout we want. If we set this too high, then it's going to cause our model to become, or if we set it too low, it'll cause our model to become slow. But if we set it too high, then, we might as well not add in the dropout at all. I think a 0.85 is a pretty good number to choose. Of course, you can kind of modify this if our model is super inaccurate, but this is a number I found to work well. Okay, so that's our second layer complete. Now we want our third layer, which is going to be the final output layer. So we'll have layer 3. Okay, it's going to be equal to tf.nn. And now we're going to use yet another function. And this one is going to be a softmax function. Now we're using softmax because this softmax function works really well with one-hot encoding. And if you remember, the outputs are going to be in that one-hot encoding format. So they're either going to be a 1-0 or a 0-1, or in case it's actually going to be 1-0 or a 0 and 578 or something like that, whatever the results of the weighting was. And like I said, this just really works well with that kind of encoding. But otherwise, we'll follow a very similar format. So tf.matrix multiplication again, we want the results of layer 2. Okay, and we want to multiply it by our weight 3 node plus our biases 3 node. Okay, and then at the very end, we want to return our layer 3. So we can just return layer 3. So at this point, we have this function that can basically take in some kind of input tensor. So this could, for example, be the training data or the testing data. And it will make some kind of prediction based on what it thinks should be the actual results by running it through these layers. And then we'll compare the predicted values to the actual values we output. And this will help us to calculate the amount of loss. And then, of course, we want to try to optimize the loss by minimizing it. So let's just make up a couple of prediction and or prediction variables for both our y-test and our y-training data. So we'll just call these something like y-train prediction. Okay, and I'm going to set my y-train prediction equal to the results of network. The input tensor is just going to be our x-training node, so x-train node. Okay, and we'll do the same for testing, but obviously it's going to be a y-test prediction. Okay, and we're going to set this equal to the results of network, and we'll input our that should be x test node. Okay, so now we have some kind of way to predict what we think we should output by running everything through this networking function. Now what we want to do is calculate the amount of loss, which is basically going to be comparing the actual output to the predicted output. So this is actually going to be a slightly different loss function to what we used in the intro to TensorFlow. This is going to be a softmax loss function, simply because we're dealing with that, again, one-hot encoding. Softmax works so well with that. So the loss is, in our case, called cross entropy. Okay, just makes more sense given what our next step will be. And we're going to set this equal to tf.losses. Okay, and we're going to go with, again, that softmax cross entropy. We don't want the sparse softmax cross entropy, we just want this regular one. And we're basically trying to compare our prediction to the actual output. So remember, keep in mind that our xtrain and ytrain nodes, not the testing ones because they're constants, but the xtrain and ytrain nodes are just placeholders. So although this won't necessarily contain a value yet, when we go to actually run our session, we will input the value, and so all of these placeholders will take on values, all of the variables will be changing, and so on and so forth. So we want to enter in here our ytrain node and our ytrain prediction. Oops, that's not train node, we want the prediction. And I've still chosen the wrong one. There should be our ytrain prediction. There we go. Okay. So again, this is just going to be some kind of a loss function. So now that we have the loss function, we want an optimizer, which is going to be used to minimize this loss function, and it's going to be using that same gradient descent. So I'm just going to call this optimizer. So optimizer is going to be equal to this tf.train and we're going to use what's called an Adam optimizer function. Okay, so it's just one of many different optimizer kind of functions. Again, I'm just showing you one way of doing things. Like I said, there's lots of ways of going about doing this. Adam optimizer is just the one that I went with, and it still works on the principle of gradient descent. So we need to put what's called a learning rate in here. In this case, we want it to learn slowly because, as you can see here, it recommends 0.001. I'm actually going to up this a bit and go with a 0.005. Okay, and we're trying to minimize our cross entropy. So .minimize cross entropy. So essentially what this is a gradient descent function. Its learning rate is going to be 0.005, so that's by how much it'll change each of the values. And it's going to change the values in such a way to minimize our cross entropy, which is our loss. And this is based on the difference between the actual output, the ytrain node, and the predicted output. Now, the last thing we want to do, before I go over everything, just kind of rehash what we've covered, is going to be to create a function that will actually predict the accuracy of our output. Okay, so I'm just going to call this something like predict or calculate accuracy. Okay, and this is going to take in an actual amount, so actual as well as a predicted amount. And this again just going to compare the actual value that we get, that we output, versus the predicted value that we want. So we're just going to convert these both into indices. So we're just going to say actual is equal to np.argmax. And we're getting the indices of our actual, and we're going to go with 1. And then we'll say the predicted is just going to be, again, np.argmax. This time we'll enter in predicted, and we will have 1. And then at the end of this, we just want to return basically the comparison of these times 100 so we can get some kind of an actual percent rather than a decimal number. So we'll just take np.sum, and then we want np.equal. Equal, let's see if I can actually spell that right. And we're taking in our actual and our predicted. In this case, I think it's actually going to want these in the opposite order, so we'll do predicted and then actual. Okay, and then we're going to divide this by our predicted.shape at the index 0. And we also want to multiply everything in here by 100. So I'm just going to say 100 multiplied by all of this. And this is just going to be a nice way to actually calculate the accuracy of our final results. Okay, so now we have a few functions to actually run everything through our network, come up with some kind of a prediction versus the actual values. We have a way to find out what the loss is, how to optimize that loss, and then a way to finally calculate up the accuracy. So all that remains now is to devise a way, probably some kind of a function, to actually run our session and then feed in some training data and then see what gets outputted. Then we can compare the accuracy of what is outputted versus what we think should be outputted. But that's what we're going to save for the next section or next 2 sections, okay? So in this section, we started off by creating our networking function, which just basically takes in some input. It runs it through each of our 3 layers by taking the output of the previous layer and using that as an input. We used a few functions that just fit our data nicely to do so. And then at the very end, it's going to return that output, which is just going to be kind of that one hot encoded data. We're using this to predict our Y training and our Y testing data, using the predicted values versus the actual outputted values. And these we don't know yet because we haven't inputted anything. So we'll remember these are just placeholder nodes up here. So we have a way to calculate the loss. We'll have to run that through, of course, our session. And then a way to optimize that loss by having a learning rate of 0.005, trying to minimize the actual loss, the cross entropy. And then a way to, again, just calculate the accuracy by entering the actual value that was outputted versus what we predicted should be outputted. So once again, I'm going to annotate these so that hopefully it'll clear up any kind of confusion. If there are any steps along the way at which you got lost, definitely go back and watch us again, because it's important that you understand what's going on here so that when we go to actually start training and testing our model, you do know what's going on. But otherwise, once you're good, I'll annotate everything at the beginning of the so that at the beginning of the next section you'll have these nice comments. I'll tell you what's going on. But otherwise, let's get to actually training our model. Alright guys, having built a few functions to actually connect all of the components of our graph and regulate the flow of data through it, we're now ready to write the code that will actually cause our model to begin training. So if you remember a couple of sections ago, we built up the actual graph components. This was the layers and the nodes. Then in the previous section, we built up our networking function, which will actually take in some input, pass that input through the different layers and output it, and then just created a couple of variables such as the loss kind of variable and the optimizer that we're going to be using. This is just going to be used to calculate the accuracy. So here we're just going to basically build up our session variable, write the code that will call upon all of these functions and pass our training and then testing data through our model. But likely we won't actually run the actual testing of the model or the training of the model. We'll just write the code to do so and then actually train and test it in the next section. So to begin, the first thing we want to do is specify how many times we want to run our data through the model in order to train it. So we'll focus on training first, then testing, obviously. So the amount of times we want to pass the data through our training model is called the number of epochs. So I'm just going to create a variable, something like num epochs. Okay, and I think 100 should do. So because our data isn't so complex that it's going to take a really long time to process, we can make the number relatively high. At the same time, this number is high enough that we are going to have our model properly trained by the end, and so should produce a pretty high accuracy rate. Of course, the higher this number, the more accurate our model will be, because it'll have more time to train, but if it's too high, then training will take a really long time. So with that specified, we can now start working on our session, and before we do so, I'm just going to import this time library, just so that we can actually time how long it takes to train our model. Now, this timing stuff is not strictly necessary. You can actually choose to ignore it completely if you want. It's just another way of doing things. This is just another component to add to our model. So I'm just going to import time, and I'll just leave it as time itself. Okay, so in order to start up our session and then start running things, I'm actually going to use this with statement, so I can say with something like tf.session as session. And this basically says, okay, we're creating a session type variable called session, and we're going to run everything within this with statement as we would like a loop or a function. It's just while we run everything within this function, we can consider this session variable to be of type tf.session. So this way, everything we write within the body of this with statement will be using this session variable here. So the first thing we want to do is, because we're dealing with a bunch of variable nodes, we'll need to initialize these. So we're going to call on tf.globalVariablesInitializer, and we're going to call .run, okay? And this is basically just going to run our global variables initializer. So that will populate these variables with an initial value of 0, and then of course we can, modify that as we go. Alright, so now if we were to just run everything, write the code that would actually start training our model, it would only train it through once unless we put this in a loop. So we'll put everything in a for loop, and we'll say something like for epoch in the range num epochs. So this is just going to say for every single epoch in the range of 0 to 100, so we'll run 100 times. And this is where we want to write our actual code. So we're just going to start by starting our timer. Again, you can ignore this timer stuff if you want, but I would encourage you to include it anyway. So we're going to call start time, and actually I should use a proper notation. So start time is going to be equal to time.time, and it's just going to get the current time. And we'll use this just to keep track of how long it's going to take to run each epoch. Now, what are we doing within each epoch? Well, we want to try to minimize our cross entropy. So this means that we're going to have to run our cross entropy and our optimizer, because this is what we're going to use to actually minimize the loss. And then we're going to have to pass in some values, because if you remember, some of these nodes we built, particularly our X-train and Y-train, are just placeholder nodes, which means they don't have a value yet, but we will pass in a value when we go to run things. So let's just go down to the bottom again. And because we'll be running 2 nodes, we'll actually get 2 outputs. Now, I don't really care about the first output, so I can replace that with an underscore here. And this just means I'm not going to store the result in a variable because I simply don't care about it. But I am interested in the output cross entropy, or the amount of loss that we have, as this loss will be decreasing as we go. We'll print that out later. I'm just going to call this something like cross entropy score. Okay, and this is just going to be equal to our session, and we're going to run. We're going to run 2 items again. The items we want to run are going to be our optimizer and our cross entropy. So you remember the cross entropy itself is the loss function, and the optimizer is aimed at minimizing this loss. Now, like I said, we'll have to pass in some values, and we'll do this via what's called a feed dict, or a feed dictionary, which is, the values we're going to be feeding in. Now, because I think the code we're about to enter is going to exceed the line count, I'm just going to put this on a new line. So I'm just going to say feed dict equals, and then in the curly braces, this is going to be the actual dictionary values itself. And the values that we're interested in this case, are going to be our xtrain node and our ytrain node. So let's just scroll down to the bottom, zoom back in. And so we'll want the xtrain node to be our raw xtrain data. So if you remember, this was, this is the stuff here, this was the 80% of the overall credit card data set that we kind of manipulated, modified a little bit. And the same with the y stuff, so we'll want our ytrain node. Make sure you're using the training nodes, by the way. We'll save the testing for a little bit later. And this will be our raw ytrain. Okay. So remember, these are the first 80%, and then the second, or the last 20%, I guess, will be used to test things out. So as of now, let's just step back for a second, and we're basically running this again 100 times. We're saying for each of the iterations, or for each of the epochs, each time we run the data through, we are just going to measure the start time, so how long it's going to take to run that particular epoch, and then we're just going to print out the cross entropy score, which will take in the current value of optimizer and the current value of cross entropy by feeding in this data. So we're going to feed this data through every single time, and so hopefully with each of these iterations, each new epoch, our cross entropy score will decrease just by at least a little bit thanks to this optimizer. And you know what, we'll probably end up printing out our initial cross entropy score, or the loss, as well as the final cross entropy score or loss, so that we can kind of compare those differences. And if the initial number is higher than the final number, then we know our model is actually working to minimize this loss. And keep in mind throughout that the cross entropy itself is comparing our y training and our y predicting nodes. So with these values being minimized and optimized, we want some way to actually keep track of how well we're doing. So we're going to print out some of these epochs. Now, printing out every single one of our 100 epochs can be tedious, so let's just print out every 10th epoch. The way we'll do this is by saying if our current epoch is divisible by 10, so if our current epoch mod 10 equals 0, then we are, let's actually use the comparison equals. We're just going to get the current time, so how long it's taken to reach that epoch. I'm going to call this timer, and I'm going to set this equal to time.time, to get the current time, minus whatever start time we were dealing with, so start time there. And then basically we just want to print some stuff out, so format a print statement. So we're going to print first of all, the current epoch we're on. So we're going to say we're currently on this epoch, and then I'm going to put something in here. I'm going to put a dot format, actually that goes outside of here. Okay, and I'll get back to this in a second. After the epoch, we want to print out the actual current loss, so the cross entropy. I'm actually just going to call this current loss. Okay, again, going to format this, and I'll come back to this. Just want to kind of format this print statement, and then after this, we want to print out the amount of time it's taken to get to this point. So we can say something like elapsed time, and again, exactly the same thing. Dot format. Okay, so now let's fill in these values. Our current epoch is going to be a whole number anyway, so no need to format that. I can actually just put in epoch. We know this is going to be multiples of 10. Now our current loss is probably going to produce some long decimal float. So let's just format it a bit. I'm going to have it to, let's say 4 decimal places should be pretty good. So we'll go 0, colon, and then points for F. We'll make sure, whoops, that comma shouldn't be there. This will just make sure that we're only printing 4 decimal places. So in the format, we want to print out whatever our current cross entropy score is. So cross entropy score can go in there, and this line is now too long. Let me just put this on a new line. As for the elapsed time, well, we're going to put in our timer. So we want to format our timer, and this may produce, again, a long decimal, so let's just format this to 2 decimal places. So we'll do 0.2f this time. And if we want to add some units, we can say seconds or something. No, that's sections, we want seconds. Okay. So at this point, that's actually all we really need to do to train the model. So once we finish iterating through these 100 epochs, our cross entropy score will hopefully be minimal, so much smaller than it was to start off with. And we can kind of keep track of things using these print statements. So that's like I said, that's pretty much all we need to do to train our model, as literally all we're trying to do is minimize our cross entropy score by modifying these variables' values, and we're going to do that using our optimizer, feeding in the raw training data and letting our network function do all the work. So if you're kind of confused about how everything is going to flow through our model, the best thing we can do is actually start here and work our way backwards. For example, we take a look at our optimizer. Well, the optimizer is using a training Adam optimizer, and it's trying to minimize our cross entropy. Well, what's our cross entropy doing? It's using a softmax cross entropy function to try to minimize the difference between our Y training node and our Y predicting node. Well, the Y training node is just basically taking in some data here as we are entering in raw Y train, and our Y predicting node is calling on our network function. Our network function is taking in the X train node, which we are passing a value for here, and it's kind of running everything through this series of layers. So it's kind of hard to see the big picture working forwards, but once we've written all the code and can start to work backwards, then it becomes a lot clearer as to why we created the functions we did, why we created all these layers, and how everything is going to flow through this neural network. Now, rather than adding the testing phase to this section, I think we're going to save all of the testing for the next section, but you know what, why don't you go ahead and run this anyway? And just kind of keep track of these print statements. So hopefully you should see a higher cross entropy score, so this current loss will be a lot higher at the beginning than it will be right at the end. By the 100th epoch, our current loss should be a little bit smaller at least. I don't know how much significantly smaller it will be. This depends on our learning rate and the number of epochs we run through. And if you're really feeling adventurous, maybe try to modify these values of our Adam optimizer and the number of epochs to kind of minimize the score. If you add more epochs, it will take longer, but will be more accurate. And if you change the learning rate, if you decrease it, then you'll probably end up getting a higher or better result, but it will take longer to train. Whereas if you increase this number too high, you might get a less accurate result, but it will train a little faster. So go ahead and give it a run through. We'll just click on the run button. And when we come back in the next section, we can write the code to actually test things out. And then the model is designed in such a way that it's actually going to it's going to train the model again every single time, because honestly, it doesn't really take that long to do so. I think if you watch the image recognition tutorial, I showed you how to actually save your model so that you can train it just once and then test it over and over again. If you want to apply the same logic in this example, that's fine to do so. I'm just trying to show you a few different ways of doing things. So already you can see that the current epoch is 0. This is the current loss, so 1.4. It's taken 3.29 seconds to do so. And by the way, don't worry about these warnings. This is just saying that TensorFlow library isn't quite as fast in PyCharm as it could be in some other programs. But anyway, so as you can see, the time is getting a little shorter. The current loss is getting a little smaller. And so I'm going to stop this section here. I'm not going to let it run all the way through, but you guys let it run through. And in the next section, we'll show you how to actually test the trained results. What is up, guys, and welcome to the final section of this tutorial. So we just finished building up a way to train our model, and we did this in this with statement. So now let's build a way to actually test the accuracy. So hopefully you guys did run it through, and as you can see, the loss started out about 1.4 and ended up about 0.82, so we know that the model is improving over time. I'm sure given more epochs, if we did like 1,000 epochs, I mean, that would take a long time to do, but if we did, I'm sure this loss would decrease even further. Now, this is really the benefit of training our model more and more. The more we expose it to data and the longer we give it to change, then obviously it's going to become better with time. But in the interest of saving you a bit of time, I'm not going to train it 1,000 times or even more. If you want to go ahead and do that, then feel free to do so. But I'm just going to finish off by showing you how to test out your model, so that we can kind of see what the end result is and how accurate the model is finally going to be. So we're going to write a little bit more code within this with statement, and then after that we can write some extra code to test specifically the fraud detection accuracy. Now, when we're printing out the current accuracy of our model, why don't we include it in this if statement so that we're printing out a new accuracy with each iteration. This will be slightly more beneficial to us, as we'll be able to see how the accuracy of the model will change as well as the loss minimized. So the way we're going to assess the final accuracy of our model is by comparing our Y, let's see, where is it? Up here. It's our Y test node, which is a constant, and that's going to be the constant outputs, against the Y test prediction, that's going to be this one, which is basically going to be the result of passing the trained data through this network. Now, if you remember, passing this data through the network as it's being trained will change these variable values. So, whereas our Y test node up here is a constant, the predicted node will be variable. So this difference between the two is going to determine how accurate our model is. So, assuming that you want to print out the accuracy every 10th epoch, or if you just want to print out at the end, that's fine. Just be sure to exclude it outside of this if statement, and actually outside of this for loop as well. But otherwise, you'll basically want to evaluate what current value each of these nodes holds. So we want to evaluate our Y test node, that's this one up here, as well as our Y test prediction. So again, the Y test node will basically have the same value before and after training. It's a Y prediction that will be changing as we improve the actual accuracy of the model. So I'm just going to call this something like final Y test, and this is going to be equal to the results of our Y test node dot eval. Okay, it's just going to evaluate what value Y test node currently holds, and then I'm going to say final Y test prediction. Okay, and this is going to be equal to our Y underscore test prediction dot eval. So basically the same thing, but obviously applied to our Y prediction. And I think I spelled that wrong. Prediction, yeah, definitely mix those around. So now with the help of our accuracy function, which we built up before, we can actually just pass in the actual value versus the predicted value, and then we can use this to test how accurate the model is going to be. So let's just call this result something like final accuracy, and there's going to be the results of passing into our calculate accuracy function first the actual value, so the final Y test. Okay, and then the predicted value, so the final Y test prediction. So this is going to output some number, probably going to be a float, and we want to print this out again after every 10th epoch. Once more, if you do want to print all this stuff out just once at the very end, then be sure to exclude it outside of this for loop, so just put it on this indentation here. Okay, but otherwise we're just going to again format some kind of a print statement, and we're going to print something like current accuracy. And then we're going to, again, format this. I think I'll go to either 2 or 4 decimal places. Doesn't really matter. It's entirely up to us. I'll go to 2 decimal places because I want a percent. So point to F, and then I'll have a percent. And then we want to do the dot format, and we want to enter in our final accuracy. Now, that being said, we can successfully test the accuracy of the overall data set. But if we want to print out the accuracy of just our fraud detection model, so basically the accuracy at which it detects just the fraudulent cases, we're going to have to write just a little bit of extra code. And it's going to look very similar to this, but will be slightly different, as we're going to have to access not our entire final Y test dataset, but just the final Y test datasets where we're dealing with a 1 on the right-hand side. So for this this final fraud-specific detection stuff, I'm just going to put this actually outside of the with statement, and our final Y test and Y prediction will hold their values even once we exit this, okay? And just doing this for the sake of a little bit of variety. Now, I'm going to stay zoomed out when I type this, because if I zoom in, then we get some of the lines of code being cut out of the window. So I'll kind of zoom in and focus on each part towards the end. But otherwise, I'm going to call this something like final fraud Y test. Okay, and then we'll have a final fraud Y prediction. So we'll actually use the same results that we calculated up here. So we'll just enter in our final Y test. That's going to be the final results, but we just want the stuff on the right-hand side, so I'm going to use some kind of weird syntax. Actually, let me just zoom in for this specific part. So in the index, okay, we're going to put our, again, final Y test, and then we're going to choose an index from this, and we're going to choose specifically the right-hand side, okay? So actually should enter the comma there, okay? And then I'm going to say equals 1. And yeah, this might look like some pretty weird notation, but basically this is just going to say that we're only interested in what's on the right-hand side of this, and we're only interested in when that right-hand side equals 1. Okay, so kind of confusing syntax, but that's all it's doing, is it's just selecting the right-hand side when the right-hand side equals 1. As if you know, or if you remember from our one-hot encoding, the fraudulent cases will look a little like this. Okay, so the right-hand side will be a 1, and that's just what we're testing for here. And, oh, this is actually saying it's not defined. Oh, I see, because we're defining it inside of our if statement here. So I'm just going to actually do this exact same thing, but outside of the if statements, so that we get a final reading. So let's just enter this here. We're going to paste it here. So this is still within our with statement. And actually, this stuff should be outside of our for loops. I'll zoom out. Let me just close up this run window. Let's just select this, and we're going to do a shift tab or shift it back. So we want it outside of this for loop, but still within the with statement. So the with statement's different in that any variables defined within it are not restricted to just being available within here. Okay. So in this case, I'm just change this to final accuracy, and this way we get kind of the constantly updated accuracy and then the very final accuracy outputted there. Okay. So now we want, again, this, and then we want the same for the prediction. So we're going to go for final fraud Y test, and then we'll go underscore prediction. Okay, and This is now going to be equal to, again, our final y-test, but we want the prediction, so I'm actually just going to copy this. And we want the index, but we still want the index specified here, so I'm just going to copy this here and paste it in here. So now that we have the y-test and the y-test prediction, all we need to do is run it through our calculate accuracy function once again. So we're going to say final fraud accuracy. Okay, is going to be equal to calculate accuracy. We're going to need to pass in our actual, so our final fraud y-test. Yeah, that's this guy. And then our final fraud y-test prediction. Okay, and at the end we can print the results out. So print something along the lines of final fraud specific accuracy. Okay, and then again the format. Let me just zoom in for this, and we'll do the dot format here. And we can do this to 2 decimal places again, just because we're dealing with another percent. So 0.2f percent, and then in the format we want our final fraud accuracy here. Final fraud accuracy. Okay, so there we go. Alright, so at this point we're actually ready to run the model. We will be training it and testing it at the same time. So even though you've already trained it once, because we didn't save that trained model, we'll just train it again. So when we actually go to start training it, I'll pause it and then I'll pause the recording rather, and then come back to it once we have finished training and then testing. But basically what we're doing here is within our the with statement, but outside of the for loop, I just basically copied and pasted this and just changed this word here. And we're getting the final evaluation of our y-test node and the prediction node, and then calculating that final accuracy that I would have calculated. All right, and then we're printing that out. And then outside of the with statement, we're testing the fraud-specific accuracy. So this is taking both fraudulent and legitimate case into account. This is just testing the fraud-specific cases and the accuracy at which our model detects those. So we'll probably get 2 pretty different figures. Now this will likely be a lot more accurate than this, again, just due to the fact that our dataset has been exposed to a lot more legitimate transactions than fraudulent transactions. As well, our test case contains a lot more legitimate transactions as well than fraudulent transactions, so there is still going to be that bias there, even though we help to eliminate it slightly using that logit weighting. But with that being said, let's give this a run through. Hopefully there are no errors. There really shouldn't be, but I'm going to pause the recording as soon as we see the first epoch pop up, and then again resume once I get the final values printed out, and then I'll kind of wrap things up there. Okay, so there we go. Current accuracy 0.15, and yeah, so I'll pause it here, let it run, and come back to you guys. And we're back. Okay, so the model has finished training again. As you can see, we're kind of getting better and better with each accuracy. We start off pretty dismal, so this was 0.15%, terrible accuracy, obviously. And as we went on, we kind of jumped a bit and then made a huge jump up here to 88, and finally we ended up about 99.39% overall accuracy. So this means that it will be able to sort legitimate from fraudulent transactions with close to 100% accuracy. Let's just call this 99%. However, detecting the fraud-specific stuff, so completely negating all of the legitimate transactions and just recognizing fraudulent transactions, unfortunately we're only about 82.56. Let's just call this 83 just to be a little optimistic. So again, this slightly lower accuracy percent could be due to a few different factors. One being that the dataset again was very heavily biased towards legitimate transactions. 2 being that even the testing data was again quite biased towards legitimate transactions. We didn't get exposed to as many fraudulent transactions as before. And 3, maybe either the learning rate was a bit too low or even a bit too high, and maybe we haven't trained it quite long enough. I'm sure if we were to run this again 1,000, 10,000, 100,000 epochs, then this current loss would decrease and we'll be able to detect even higher accuracies. But otherwise, that is pretty much it for the basics of building a fraud detection model, at least with credit card fraud. Now, like I said, I'm sure this is just one of many, many different ways that we can go about building this model. Perhaps if we added more layers, it would become a little more accurate. Perhaps if we use a different number of cells for each of the layers, again, it could be more accurate, less accurate. So kind of playing around with these parameters does take a little bit of work, and not quite guessing and checking, but a similar sort of concept is needed to kind of optimize your model. You just need to play around with the parameters a little bit and see what works, see what's improving your model, what is not improving your model, and then work towards obviously improving things. Some models, if you tailor them carefully, can achieve pretty much 99% accuracy or higher across all boards. But of course it would help if we had access to a little more data. Otherwise, with that being said and our model complete, I'll just kind of run through things with you from start to finish in the order in which we implemented everything. So we start off just by kind of getting a little more familiar with the dataset. We had about a dataset of about 284,000 transactions, something like that. Again, only little less than 500 of them were legitimate or were fraudulent, and the rest were legitimate, so there is that heavy bias to deal with. Now, the dataset itself was separated into a few parts. We had features v1 through v28, which were just basically a bunch of features of the transaction itself or transactions themselves that were converted into a numerical input. So this may honestly be the hardest thing about building up this model, is getting access to that data and then using the correct function to turn the actual features of the transaction into numerical data. But once you can do that, and we already have some data set to do that for us, that is kind of taken care of. Okay. Then we worked on kind of splitting up our data into these 4 sets. We first shuffled it, converted it into that one hot encoding, normalized the data to make it between 0 and 1. Separated out our x and y values, so remember the x was the features v1 through v28, and the y was just that one hot encoding of class 0 and class 1. After this, converted it to an array of floats, and then basically separated out our training and testing data. The first 80% of the data was allocated to training, and the remaining 20% was for testing. After this, we figured out a way to basically print out our ratio. We got basically 0.17% were fraudulent, and the rest were legitimate. So we had to kind of try to balance that back out with what's called logit weighting. So we basically multiplied all of the fraudulent transactions by this number, about 578, or 1 divided by 0.0017. to make our model pay closer attention to the fraudulent transactions. So with a higher weighting, our model will recognize the fraudulent transactions more, and will kind of pay closer attention to them just because this weighting is so much higher than the regular one. Although, as we can see, it wasn't quite as accurate, it wasn't 100% effective, seeing as we have a lower final accuracy for the fraud-specific stuff. But, I mean, no model's perfect and can always be tweaked and improved. Anyway, after this, we worked on actually building up our computational graph using a bunch of TensorFlow functions. We just specified some constants up here, number of cells in the first and second layers. The input dimensions are going to be that those X arrays of about features v1 through v28, plus stuff like the time and the amount. And then the output was just going to be the 2 cells, which are, I guess this one here, it's just going to be the 2 cells for that one hot encoding. We created some nodes here, the placeholder for our x and y train, some constants for our x and y tests, and then about 3 layers in our total neural network. So one was for the input, then we passed it to the second layer, and finally the third, which will output, again, either that 0 or 1. Next, we defined a few functions to first help us pass everything through the layers. This was our network function. We have just a bunch of other functions, sigmoid, then a dropout and a sigmoid, and then a softmax, and these will kind of help fit a line through our data so that we can work on minimizing the loss. Next, we came up with some prediction variables. These were what we would predict without training our model. So these are, or rather, these are the values that we would have altered towards the end, whereas the actual test up here, the constants, these are x and y tests, these were the actual should be outputted kind of values. Next, we defined a cross-entropy variable. This is to measure the amount of loss. This is what we're trying to minimize using our optimizer. We just chose an Adam optimizer here. And this last function was just to compute the accuracy at the very end. And then finally, in the last couple of sections, we built up the way to actually train our model and finally to test it. We're training it basically 100 times, running the data through our model 100 times using the raw X train and the raw Y train data, which we modified at the very beginning. Came up with this new cross-entropy score with each epoch, and then every 10th epoch we're just kind of printing out the time, the current epoch, and the current loss value, as well as towards the end the current accuracy of our model. So we saw that drastically improved over time, as well as the cross-entropy score itself lowering, which is exactly what we'd want. Then at the end, once our model was fully trained, so exited the for loop after running 100 times, we're printing out the very final accuracy recording that we, or based on our final values in the y-test node and the y-prediction node, as well as the fraud-specific values. So this is just the overall, the accuracy of the overall data, so legitimate and fraud, how good is our model at sourcing legitimate versus the fraudulent stuff, whereas the fraud-specific accuracies were just focusing on how well it detected just fraud versus fraud and legitimate. Alright, so there you have it, your complete fraud detection model. Like I said, there's always a lot of room for improvement. It's just one of many different ways we can build this. Some possible things you might want to try out are maybe modifying, first of all, the number of cells that we're adding to each layer. So you could try modifying these values here. Wouldn't recommend modifying the input or the output because those values should stay the same, but maybe try playing around with these values, try greater values, values that are less than these, and so on and so forth. Another way to maybe improve, or it might actually be a detriment to your model, would be to apply a slightly different weighting. So a higher weighting will cause our model to pay a little more attention to the fraudulent data, whereas I wouldn't recommend going any lower than this, or else our model won't recognize the fraud stuff as well. Other ways we could modify it would be to maybe add in a fourth layer. So between our input and the output, add in like a layer 2.5, I guess, or I guess make that new layer layer 3 and our output layer be layer 4. Although this being said, if we try to make our model too complex, it's just going to take a really long time to run and to train. So for our case, this works pretty well, but it doesn't hurt to try things. Another way we can change up the model is to change the specific functions we're using. So we're using a sigmoid, then a dropout sigmoid, and a softmax. I would recommend finishing up with a softmax just due to the one-hot encoding. And in our case, I think the sigmoid probably fits the data a little better. But, you know, there's a few different functions that we can try out. Maybe using a different function would produce a different output. And then finally, the stuff we've been over before, maybe a different optimizer altogether would produce different results. Obviously, a different learning rate would help your model to learn faster or slower, and the number of epochs, a higher number of epochs, will make your model more accurate, but will also take longer to train and to test. But with that being said, I'll leave you guys to kind of play around with things a little bit on your own. We have lots of other machine learning models and tutorials to build. So once you're comfortable with this, we can move on to some of those. So be sure to check out the other models, and as always, we really appreciate the support and hope you enjoyed this tutorial and managed to take at least something from it.